So today we're going to be building the following beautiful puppy you see on the screen right now. And this absolutely breathtaking visualization or animation is actually visualizing a times table, believe it or not. In that what's happening is that it's showing what a 2 times table looks like, or a 3 times table, and a 5 times table, and it's looping through all of those. And what we're doing is that we're taking each point along a circle. So we take a circle and we say, okay, divide it into 100 points. And then multiply each point by a particular number, which would represent the times table. So imagine you took point 1 and you multiplied it by 5. So you drew a line from point 1 to point 5. And then you took point 2 and you multiply it by 5. So you draw a line that joins point 2 to point 10. You take point 3, you multiply it by 5. You take a line that joins point 3 to point 15. And you keep doing this, and you increase the number of points, you increase the number that you're multiplying by, and you get this beautiful image. This is inspired by a video by MathLogger on this topic, and I'll keep a link to that video in the description. But without further ado, let's jump into it. So let's explain some of the math that we need in order to do this. We're going to start with a simple circle, and we're going to choose two numbers. One of the numbers is called our factor, which is like our times table, right? Let's take 2, for example. And the other one that we want to look at is our, or number of points, right? So let's just call this points over here. And let's say I'm going to start with 4 points. What we are going to do is we're going to label these points. Starting, we're going to equally distribute these points along the circle. So these are my 4 points. And we're going to label them from index 0. So this is 0, 1, 2, 3. And we're going to draw a line from each point to each other point based off of our factor. So we're going to say 0 times by 2, that's equal to 0. So we're going to draw a line from 0 to 0. There's no line from 0 to 0. Okay, then we're going to say 1 times by 2. That is equal to 2. So we're going to draw a line from 1 to 2. Then we're going to say 2 times 2. 2 times 2, that is equal to 4. Now, there isn't a 4 here, but this loops in the sense we go 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. So this is going to go from 2 to 0. Then we're going to go to 3, and we're going to say 3 times 2. So sorry, as I dumped over that, but this is 4, right? So because 0 corresponds with our 4, that's where it's going to go. Now we're going to have 3 times 2, that is equal to 6. And our 6 is over here, as you can see, right? Because we went 0, 1, 2, 3, 4, 5, 6. So we're going to draw a line from point 3 to point 6. And then we loop again. Now there's another way that we could find these indices, right? Especially because this is going to keep going. We're going to go eventually to like 1,000,000. And then like, where is index 1,000,000 on a circle with 4 points? And this is where the idea of modular arithmetic comes in. And what that looks like is the following, as I just make this all a little bit cleaner over here. So this is 3, this is 4. What we can do is, say we're looking at point 6, right? So we knew that 6 came over here. And we want to find a way to map that to, sorry, this should not be 4. This should be 1. So if we want to map point 6, so we can take 6 modulus the number of points, 4. So 6 mod 4, that is equal to 2. Because what modulus is saying is, okay, 6 divided by 4, remainder what? So 4 goes into 6 one time, remainder 2. And now this will apply for anything. If we take 8 mod 4, that's going to be 0, because 8 divided by 4 is 2, remainder 0. But 9, for example, 9 mod 4, that is going to be equal to 1, because we're going to get 9 divided by 2 is 2, remainder 1. And we can see that, right? So if this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And we can see that we get 9 at index 9, we're getting to 1. Okay, so that's a way in which we can keep the indices. So this is pretty much it. All then we need to do in order to get the animation we were seeing was increase factor and increase number of points. There's one other thing we need to do, and that is because we're dealing with Cartesian coordinates in P5, we need to be able to express them, we need to be able to like take these points and say, okay, what is their XY coordinates? So if we have these points, let's go for a different number of points here. Let's say we have 8, okay? So if we have 8 points, then we know that the angle between each point, if we want to equally distribute them amongst the circle, it's going to be 360 over 8, which is equal to 45. So it means for every point, I'm going to start at 0. I'm going to rotate 45 along the circle. Then I'm going to rotate another 45, and then 45, 45, 45, 45, 45. Those will be my points, and I have 0, 1, 2, 3, 4. Now, how can I find the coordinates of these bad boys over here? And the way we do that is through the polar coordinate conversion. Let's take this color. So we know if we have our origin over here, this point is very simple, but let's say this point, for example, point 1. If we want to know what our XY coordinate is of point 1, we can use trig in order to do so, right? In the sense that we know that there is going to be our x, and if this is our y-axis, rather, over there, that is going to be our y. So that corresponds to that height over there, and the height of this triangle and the width of the triangle. We know that this is 45, right? Or we can say, so that's our theta. So now in order to find what our y or our x is, we know that the sine of 45 is equal to your opposite over your hypotenuse, which is y over r. This is y, this is r. And we know that our r, whatever we've defined our radius to be, right? Let's say our radius is 200, whatever it might be. So we know that our y is equal to r sine of 45, or sine of theta. And our x is equal to r cos of theta. Okay, cool. That is pretty much all the math that we need to know in order to do it. Let's jump into some code and get it done. Okay, let's code this thing. So I'm going to say function setup, and I'm going to go ahead and create a canvas, and I'm going to make it window.innerWidth and window.innerHeight. Then I'm going to go into function draw. There will be a link in the video description to follow along. And, oh, that's wrong, function draw. And I'm going to give it a black background. And I'm going to say strive.draw tick axes in order to get our grid lines so we can see what's going on. Okay. Next, what we're wanting to do is move our 0, 0 point into the middle, because currently it's at the top left corner. We want to have a circle that's centered. So in order to do that, I'm going to say strive.translate to width over 2, height over 2. Translate will just move, so we'll move the origin to these coordinates. We're using strive.translate in particular here, and you can only use this function if you're in this environment from the link in description, because we want to have kind of like these special functions and make it easier to see what's going on. So strive.translate, width over 2, strive.draw tick axes. Now let's draw this circle. So let's say our radius, let's make it 200. We can draw a simple circle by saying 0, 0, and radius. Let's see what happens. Perfect. Oh, not perfect, because this is a radius of 100. This argument over here specifies the diameter. So if we want to get the radius, we say radius times 2. Let's make sure that works. And let's only get the outline. So I'm going to say no full. And I'm going to say stroke, which will define the outline. I'm going to say white. Let's see what happens. Okay, perfect. We got a circle. Now let's get all of these points along the circle, right? For whatever our number of points is. So we're going to make a variable called let number of points. We can do shorter, we can just say num points. And let's say we're going for 8. Now, we want to loop through each one of these points. We want to find the angle at which that point is, and then translate it to an xy coordinate. So we're going to say for let I is equal to 0, I less than num points, I plus plus. And then we want to do something else. We want to find what an x is. X will be equal to something. We want to find what our y is. Y will be equal to something. And then we're going to plot a circle at that point. It's x, y, and we'll make it like something like 10. How do we find this x and y? So we know it's going to be something along the lines of radius times by the sine of something, or sorry, for x it's cos, and radius times by the sine of something. The way in which we find the angle, right, we know that the first point, angle will be 0, right? So we're taking, technically going 0, the 0th index times by, let's do angle per point or something like that. So let's say angle is equal to 360 over 8, right? That means for every point, we're going to move 45 degrees or 360 over 8 because we're going to change our number of points. So the first point is 0. Oh, angle is 0. The next one is 45, then 90. What you're doing is you're actually just taking index 1 times by angle. 1 times by 45, 2 times by 45, 3 times by 45. That gives you the angle at that particular point. So we can say I times by angle, and I times by angle. And now with that, we should get our circles. Perfect. And we get our circles. Why are we getting a weird circle over here? Something's a little bit weird here. Because, like, you can see that these two circles are acting quite strange. 360 and make sure num points. That won't make a difference. Maybe it rendered discriminant. Oh, I know why. Because we're in radians. By default, we are in radians. So we actually want to move this into degrees. If this was 2 pi, then it'll be fine. But because we're working in degrees, that should be the reason why we get that. Let's refresh because I don't think that ran. Come on, show me the money. What's happening? Oh, it didn't say properly. Angle mode, degrees. Degrees. Come on. There we go. Okay, now it's nicely distributed and we're getting what we expect. The next part is then we want to follow the algorithm of taking 0 times by our factor. 0 times by 2 is 0. 1 times by 2, 2. 2 times by 2, 4. And drawing the lines then connecting those points. So let's make a variable called factor, let factor, and let's start with 2, for example. And we then want to loop through, right? So this is our index over here. And then we find our destination index by multiplying our current index by our factor. So we can say let destination index is equal to I times by our factor. Now we, though, need to translate that because sometimes it's going to go over, right? Like if we're at position 7, for example, and 7 times 2 is 14, where is that? We need to do the modular arithmetic that we did previously. So we need to say that modulus the number of points. That will give us the correct destination index. But now we need to translate that index into an xy coordinate. And we already have a system of doing so, right? If we have an index, all we need to do is multiply it by that angle and put it in cos and times by the radius to find the coordinate. So we can do the exact same. So I can say let xd is equal to radius times by the cos of destination index times by angle. And I can say let x or yd for y destination, radius times by the sine of destination index times by the angle. With those two, we can then draw a line. We can say, because the line takes x1, y1, x2, y2, and draws a line connecting those 2 points. So we can say x comma y and xd comma yd. And let's see what happens. Okay, cool. We are getting something that's looking pretty dope. Let's increase the number of points and see what happens. Even better, we're going to make the number of points equal to mouse x. I wonder how this is going to... Let's start slow. Let's just go number of points 100. And then we're getting... And we can see this cardioid shape, which is forming now. A cardioid like this, it's called a cardioid because it looks like a heart. Or the heart is like, regardless, this is the cool shape it's kind of forming. We could probably, if I did mouse X, then as I move my X, we will increase the number of points over here. Yeah, there you go, right? Can see how cool that looks. We could also do something pretty cool on saying, letting our factor, actually I'm not wanting to do that just yet, because the next part is just getting this kind of motion that we saw previously working. So how do we do that? The way that's happening is actually just by increasing our factor continuously. So if I make factor a global variable instead, and I'll say factor is equal to 0, and then if I just increase factor plus equals 1 every time, then that is literally going to be it. Notice the shape that we get, or what happens. Right? If I decrease my mouse X until we eventually get nothing and increase it all the way, you can see these awesome things that start happening. You can play around with this a bunch. Let's remove the tick axes. Now, there's one cool thing that is almost counterintuitive about this. So cool. I'm already just getting... I love how the circles like move around a little bit towards the top when you do that. The one cool thing I'm wanting to show is that we don't need to increase factor by a discrete amount. Discrete meaning like 1, 2, 3, 4, 5, 6. It can be continuous in the sense of we could increase factor by like 0.001. And so you're no longer looking at the 1 times table, 2 times table, 3 times table. All of a sudden you're looking at the like 1.456 times table, or the 7.2891 times table. So notice what happens when I say 0.123, for example. So now I'm increasing by that amount. And now we get this much smoother kind of image, which is actually forming. Let's do something like 0.01. And you're going through these fractional increments for each one, and you can see now how nice that kind of looks as it moves across, right? Because now we're looking at like the 0.005 or 0.5 times table and 0.6, 0.7, etc. And what is happening here? Oh, there we go. Now it starts. It's just going very slow. Let's go like 0.01 rather. This might give us a nicer looking shape. Yeah, there you go. And then boom, you can see that would be the 2. And now in the 2 times table, that would be 3. And you can kind of see it as that goes. Let's put it at 0.1. And now you could do a whole bunch of stuff with color here. You can make the color of the lines dependent on, you could just like loop through the RGB color system. You can make the color dependent on their length from each point. So you can make it dependent on their angle to one another. There's 1,000,003 things that you can do to play around with color. But what I just find amazing is how simple this code is. It's just like, what have we done this in like 30 lines of code? And you can make this probably more efficient by introducing functions. And we have this just beautiful visualization here. It's really astounding. Yeah, thank you for joining me. And I'm keen to see what you guys are able to create with this.